Solution continued. Finding the table of possible quantity of roots for this polynomial set equal to 0. Let's see. I want to make sure we get that written exactly right. Okay, so what we're going to do now, we're up to step 3. The previous video took us to step 2. Here we're going to find the number of variations in not p of x, but p of negative x. Okay, so let's write p of negative x. All we have to do is go through this p of x. This is p of x right here. And we just have to change the sign in front of the coefficient for every odd power. See, we start out by saying that this is equal to 3 parentheses negative x parentheses to the 6th plus 4 parentheses negative x to the 5th plus 3 parentheses negative x to the 3rd minus parentheses negative x minus 3. Okay, so we go ahead and change the sign in front of, when we simplify it, it's the same, well, you'll see, I'll show you right now. Negative x to the 6th gives you an even result, a positive result, because it's a negative base raised to an even power. So you get positive 3x to the 6th. But the negative x base raised to the odd power 5th gives you a negative result. The negative sign comes out in the front, so we get minus 4x to the 5th. And then the odd power 3 brings a negative sign out in the front, 3x cubed. Then the double negative makes a positive, minus 3. So essentially, we took the original p of x at the top of the video, and we just looked at, well, we're missing something, aren't we? That was, let's see, we forgot plus x minus 3. Okay, now we're cool. And we went through, every time we had an odd power of x, we just changed the sign in front of the term. So that 4x to the 5th became negative 4x to the 5th. And that positive 3x to the 3rd became negative 3x to the 3rd. And that negative x to the 1st became positive x to the 1st. Everything else stayed the same because those were positive. Now we change, those were even indices. In even powers. Now we're going to count the number of sign variations. We start positive, we go right here, boom, right away, we change signs. So that's going to be number 1, sign variation. Let's continue, we're negative now, going on, staying negative, boom, right there. Right there we've changed to a positive. That's sign variation number 2. And now we go from a positive to a negative. Boom, there's our last sign variation. That's the 3rd one. So that implies that we have 3 variations in sign. And the number of variations for p of negative x gives us the following result. We're supposed to take the number of variations and subtract 0, 2, 4, 6, 8. Stop when the answers start becoming negative. Okay, so there's 3 minus 0 equals a possible quantity of 3 negative real roots, or the other possibility would be 3 minus 2. See, we subtracted 0, now we're subtracting 2. That gives us 1. That's the other possibility, 1 negative real root. Or, let's try another one. We subtracted 0, we subtracted 2. Now we're going to subtract 4. That gives us negative 1. Oh, okay, stop, right there. We don't take negative results. We're done. We're just using this result. Okay, so those are the possibilities. Let's go ahead and make a big box around this. Those are the possibilities for the quantity of negative real roots. Okay, so on the previous video, we took the same polynomial. We found there could be possibly how many positive real roots. We found, because there was only one sign variation, that gave us a possibility of only one positive real root, and that meant that because there was only 1, 0, there was nothing to subtract 0, 2, 4, 6, 8 from like we did here. Here we were able to subtract a few of those, 0 and then 2. Now we're going to take all of our results and we're going to summarize it all on a table with step 4. Making our table here. Okay, now the first column is going to be the positive real roots. Okay, the quantity of positive real roots. And to that we're going to add the quantity of negative real roots. And to that we're going to add the quantity of imaginary roots. And together that will give us our total number of roots, which we know, including multiplicity, will be the degree of the polynomial. These are complex roots because we added the imaginary ones to the real ones, so it's a total congregation of complex roots. The degree of the polynomial they gave us was 6. We can start filling in this table. Let's make this table. It's not going to be too big. The reason it's not going to be very big is because we already figured out there can only be exactly one positive real root. So let's put that number 1 here. And then in this row, we're going to add this to the first possible quantity of negative real roots, which was 3. Okay, now we know the total is going to equal 6 because it's a 6th degree polynomial. So if we have 1 plus 3, that makes 4, then that means that we're going to have to add 2 more, and that's going to be the imaginary roots. And don't forget, imaginary roots come in pairs, because if you have one imaginary root, you automatically have the complex conjugate of that root. Okay, so 2 makes a lot of sense to me. Okay, the next row, we're going to go with the 1 positive real root, because remember, that's the only option we have for positive. And then we're going to use the second option we got right above this for negative real roots. There was a possibility of having 1 of those. Okay, and we know that they're going to all add to 6, so we have 1 plus 1 is 2, plus some other unknown number for the quantity of imaginary roots has to equal the degree 6. So how many does that leave for us? That leaves 4. There has to be 4 imaginary roots. Again, that makes sense because it's a multiple of 2. These guys come in pairs. The imaginary roots come in pairs. So this is the end of our table, and we are finished. In this situation, you can see that either we're going to, if we solve this problem, either have 1 real root with 1 positive real root and 3 negative real roots and 2 imaginary roots, or the other scenario possible is 1 real positive root, 1 negative real negative root, or added to 4 imaginary roots.